Hi, my name is Mihai Kiveti, and I'm going to talk about Retrieval Augmented Generation in practice, how to scale GenAI platforms with Kubernetes, LangChain, HuggingFace, VectorDBs, and other such tools. Here's the idea. I'm going to introduce large language models and their limitations, and how to use Retrieval Augmented Generation or conversation with your documents or your data to overcome some of these limitations. A bit about myself. I'm responsible for large-scale cloud-native and AI solutions at IBM. I'm a Red Hat certified architect, and I'm driving development of Retrieval Augmented Generation platforms that leverage watsonx, vector databases, LangChain, Hugging Face, and open source AI models at IBM. Let's talk about large language models in practice and some of their limitations. I like to think of an LLM as similar to your phone's autocomplete, or better, a mathematical or programmatic function, f of x equals x prime, where the input and the output are strings. So think you're writing Bash, you're writing Python, you're writing any other code in any programming language, and you're defining a function. That function has an input and an output. That's kind of how an LLM works. You call it once and then it dies, right? It doesn't remember anything. It doesn't have any kind of global variables for it to learn. It's really a one-way function. A more accurate representation is to think of that function of taking multiple parameters. So for example, it takes training data. So that's the input, right? That's baked in the model along with model weights and those kind of things. It also takes parameters, things like temperature. How spicy do you want your answer to be, or how hot or how creative? And it also takes an input string. That input string typically consists of a prompt, like, you are a helpful and useful agent. You'll respond to me in a certain way. And then some context. So the data that you want that model to act on. It doesn't need to have a context. Sometimes the question or the prompt can be, what's Kubernetes? But if it has a context, it can be more like summarize the following document, and then you give it a bunch of text. That's your context. And you get back an output string. So you're really performing a transformation, a string transformation in these large language models. And that function can process a maximum of token limit. That's a total input and output, usually about 4,096 tokens, although there are models that take 100K, Claude, for example, but typically it's around 4K tokens. That's 3,000 words in English, but it's fewer if you're writing in Cantonese, Chinese, Japanese, any of these other languages. So think about it as a one-way function. It runs once, and it transforms one bit of string into another bit of string based on the data that model has seen. That's the training data, and a couple of other things that you define in the model parameters. So here's what the model doesn't do. It doesn't learn. It's not a brain. It's not really artificial intelligence. It won't learn from any of these interactions unless it's specifically trained or fine-tuned. So, whenever you're talking to any of these online, let's say, chatbots that support large language model transformations, a lot of the learning is done with trickery, right? It's really the API or the user interface of that model that remembers the text that you've said, stores it somewhere, feeds it back to that model. So the next prompt to that model won't be your question. It will be, you are engaging with a person. That person has previously said, give it a text, and then it enters your new text. The problem is that only works within the context limit. So if you remember in the previous slide, the token limit there, it's about 4K input and output totals. So you're using usually a moving window protocol to keep track of what the user has previously said. But once it exceeds that limit, well, the model will forget. Try it. Go to any of these online services. Say, my name is Mihai, and then give it 40 pages of additional text and ask, what's my name? It forgets, right? So here's one of the reasons we're using Retrieval Augmented Generation to create a memory for the model. So remember, it doesn't learn, it doesn't remember, it also doesn't reason, right? Give it your name, ask how many characters are in your name. It doesn't do math. It's really just fancy autocomplete. Very good autocomplete, very useful autocomplete. You can use chain of thought to simulate reasoning with that, and you can verify the steps, and there's a lot of trickery that you can do with these models, but that's one of the limitations here as well. It also doesn't use your data. So how do we get a model to use our data? Well, if we have a lot of money and a lot of GPUs, we can train a model on our data. It's very expensive, right? And it takes a long time. And the results you get are sometimes unpredictable. So training isn't really accessible to most. And it might not be the best approach to most use cases. Let's say that you're interacting with documents from the user, right? You're creating a service, somebody's uploading their document, you want to interact with it. Well, you're not going to train them all and say, hey, can you please wait a couple of months for me to train them all, or weeks or whatever, depending on the type of model you're training. Not really achievable. So to use a model with your data, we can use Retrieval Augmented Generation that takes the document, feeds it into a vector database, and from there inserts the context into the prompt every single time. Also, models don't use the internet. It's like, oh, AI is going to go rogue and, it doesn't do anything. The model will only perform this text transformation once, and then, that's it. It doesn't have the capacity to use other REST APIs or calls. So whenever you want the model to use third-party data or information or REST APIs, again, you're applying this RAG pattern. You're doing it outside. You're using Python, Go, some other programming language. You're writing code to feed that additional data and interact with APIs. So what are the key use cases for some of these, large language models? Well, you can really break them down into question and answers. So, answer a general knowledge question, information extraction. And here's the cool stuff about large language models. They tend to perform quite well at some of these specialized tasks where you would previously use a specialized model that you would train, that you would, really focus on. You can use it for information extraction as well. You're just giving it a prompt. So literally all of these use cases are differentiated just in the prompt that you give them all. So for information extraction, you're giving it a prompt like extract all the names of the people in this document, and it will do information extraction. And you can rephrase that in 50 different ways, hundreds of different ways. Classification, same kind of concept. Is this text or factual, is this text factual or an opinion? Or, detect if the sentiment in this text is positive or negative or something like that. And just by using that prompt along with your context, your text, it will perform classification. Same for summarization. You're literally feeding the function, the model, a text. And that text starts with summarize the stuff below, or summarize the text below, or you're an academic professor and you're summarizing documents and using an elevated language. There's different ways of writing these prompts, right? Sometimes you may want to even say, summarize the text below. You give it the text and then you say summary, semicolon, and that'll make it, perform better in some cases. Same for generation. You're just saying, write something, give me something. So generation, can be even, translate the sentence into Irish, right? That's an example. But the best way to think of a model is like this. So every time you're using an LLM, think of adding a modem to your architecture. The latency is really bad. The performance, they're very slow and they're very expensive to run. In fact, I don't think this is a good example because this is a 56K modem. I used to have one of these and, they had Linux support and you could connect to the internet using Linux and you'd pay a lot of money and you could chat on IRC and all that stuff. But you could chat with multiple people in real time. So the performance of a 56K modem is beyond what you get with today's LLMs. In fact, just some basic calculations here. they're more like a teletype. So if you have your own GPU, let's say I'm paying 20K a month for a dedicated A100 GPU, and I'm running Llama 70B, which is the 70 billion parameter model. I'm probably gonna get about 1,200 words a minute, right? It is gonna be slow. It is not gonna perform as well as you think it will, right? And you can only connect to that model with one instance, right? It does its job, and then you're queuing other requests on it. Now, there are ways to speed some of these models, like quantization, and you're, going to run a 13 billion or a 7 billion parameter model, or you're going to run multiple models, or you have multiple GPUs, or you're using a service, and they're paying a lot for it on the back end. But the reality is that these models really don't transform text that fast. So if you want to build an application that processes credit card transactions, so like first of all, due to hallucinations and other kind of issues in the generation, that's not a good use case. But also the performance. If you're processing log files, for example, yeah, you could use a LLM, but if you're really processing hundreds of thousands of lines of log files a minute, this is probably not the best option. A very small dedicated model or something even binary, might be more appropriate. And you also need to think that most of these models have a token limit as well. So you can't just go off and say, hey, here's my log file, go process it. You need to feed them a bunch of lines, and they're not going to be able to perform those correlations. So there are quite a lot of limitations today to these LLMs. They're evolving. If you look at Llama, somebody's already put out Longma, which has 8K, 16K context windows, although the performance, as in the quality of the output, kind of degrades once you go over that 4K token window. And even commercial models have started to come up with 16K windows for Claude, for example. It's 100K, although even that is a limit for most of these use cases. So let's talk about getting these LLMs to work with our data. We have a number of options. Here's 3 basic choices. We can train them all. Very expensive, takes a long time. We've talked about this. It's not really going to deal well with real-time data. We can fine-tune them all. Again, that's also expensive, but it's achievable. Maybe it takes a day, right, on a top-tier GPU cluster. It's achievable. And you can, if you look at some of the papers, even with 1,000 good examples, you can do a good job on fine-tuning. However, if you have a lot of data, it's not really achievable. It does take time, so for real-time use cases, still not an option. So what are we left with? Well, prompt engineering, where we're inserting the data into prompts every time to a process called Retrieval Augmented Generation. It's cheap. You can work with vast amounts of data, your databases, APIs, even your documents. And we can use a couple of tricks to make them even more useful. So vector databases are used for some of these RAG patterns. You don't have to use it, right? You can literally use Lucene or Solr or Elasticsearch or Mongo or any database to perform RAG. You don't even need a database. You can use Face or any of these other tools. But vector databases help because they allow you to perform a vector search. So think about it like this. If you do a SQL search in a database and you say, I want to look for the word sky, right? It'll find the word sky, maybe, skies, that's it. But if you search in a vector database, you search for sky, it will find back blue because it's related in vector space. That's how you can think about it. They're fast. They can store huge amounts of data, and they allow you to perform this, near vector search on embeddings. And you can overcome a lot of your model limitations by first storing your data into a vector database. So let's talk about that. How does that actually look like in practice? Here's a diagram that shows a very basic RAG pattern. The user as a question. Let's say, for example, I'm going to ingest a document which is the Form 10K of a company, right? And in this Form 10K, they have financial information about the company, their products, their business. And it's a huge 200-page PDF document. I'm going to take that PDF document. I'm going to transform it into text, because remember, large language models only deal with language, text. They don't understand binary data like PDF files. So I need to transform it from PDF to text. Well, that's the first problem, because that conversion is going to be imperfect. So now I have a 200-page text document. Hopefully, I'm also transforming embedded tables and images, and I'm cleaning up that text. But remember, our LLM has a token limit. It can't process my 200-page document. Whoops, well, that's a problem. So I'm going to chunk it. So I'm going to split it into overlapping segments. I'm going to enhance those segments with some metadata, and I'm going to store that. But that's text. So I need to store it in a vector form with embeddings. So I'm going to use an embeddings model. Here you can see I'm using one from SentenceTransformers. You can also find this on HuggingFace. All mini LM performs reasonably well. There's better models out there, but they tend to be slower. And this will generate vector embeddings of my text. And I'm going to do the same thing of the question. So now I have, remember, you have your document, which you've converted from PDF to text. You split it into chunks. You've added those chunks into your vector database. And the vector database allows you to do a near vector search. So now I'm going to vectorize my question. For example, what is the business model of this company? Right? I'm going against the Form 10K documents. That question will be vectorized as well using the same embeddings model. And now I can retrieve similar documents, or I can retrieve near vector data from this vector database with my chunked embeddings. And I'm going to retrieve top 10, top 20 results. And then I'm going to feed those results into an LLM. So for example, I'm going to use Llama. Again, 4K input and output total. I've got about 10 results of about 300 words each. So about 3,000 words go into my model, these top 10 results. And now they're summarized by this model, and it comes back with the answer. I will also render back to the user, hey, here's the top 10 results that I've used, along with their probability based on what the vector database tells me, because you want the user to understand what documents formed your answer. And I'm going to benchmark the performance of my summarizer so I can use it further. And maybe I'm going to ask my user for feedback so I can use that for fine-tuning my model. So that's kind of how a RAG pattern works. I might also insert a re-ranker here after retrieving the data from my vector database, so I can re-rank and I can enhance some of this with metadata. So it's quite simple, right? Think of it as, Solr search or Lucene search or Google search, right? You're searching for a document based on a question, but you're using a vector search, which is more powerful. You're feeding top 10 results into your model, and the model is going to use that along with its data that it was trained on to generate an answer for me. And this is how a lot of these, AI enhanced search engines work as well. AI doesn't know about search. You're still using the typical search. You're feeding those results into a summarization or into a text generation prompt into your LLM. Let's talk about the vector database as well. Here's kind of how those documents get chunked and vectorized. So think about it like this. You have documents in multiple formats: PDF, text, docx, databases, and so on. LangChain is a powerful tool that lets you do a lot of things with LLMs, but also process text. You can do this by hand, right? There's nothing stopping you from using, MuPDF or any of the PDF libraries, or, even if you're processing docx, just, unzipping it, processing the XML manually and extracting it, but LangChain kind of helps you automate a lot of these loading activities and conversion activities, although it does have limitations. So when you do PDF to text with LangChain, it doesn't, do OCR, it doesn't process images and tables well, and there's some limitations there, and you need to be aware of them. And you can write better converters as well for this step. So you're taking the data, user data. Maybe it's a PDF file, maybe it's hundreds of thousands of PDF files, maybe it's databases, maybe it's a mixture of things, and you're converting them to text, splitting it into overlapping chunks, converting those chunks into vectors, and loading them onto your vector database. Now, something to consider here as well. Your company, or you might have established search databases. A lot of folks use Elasticsearch or Mongo or these kind of things for a search, and now they're also adding vector support. So your choice of vector database really does matter. There's pgvector, which has an interface to PostgreSQL, which is awesome, although the performance seems to be quite poor these days. You also need to look at where your vector database is going to run. Is it going to run in cloud or maybe locally on Kubernetes? Maybe these are confidential documents. You don't want everybody to have access to them. You're running a local model. You're running a local vector database. Weaviate tends to scale quite well. I've deployed that on Kubernetes, and you can really do high availability and chunking, and you can run 9 instances on it, and it comes with a Helm chart. It is quite a good product from what I've seen. And there's other options as well. Embedded databases like ChromaDB tend to be really awesome for development, but maybe harder to scale. It really depends on your use cases. So do a bit of research, take a look at some of the options, try them out, and think of the scaling and operational aspects as well. So here's a couple of tips about scaling retrieval augmented generation. First, your vector database is going to be very important. Benchmark it, test it, scale it, look at backup, look at resiliency, encryption, deduplication. Think about, all of the things related to non-functional requirements and operations. Fine-tuning. How will you collect the data used for fine-tuning? Governance and model benchmarking. So how are you testing your model performance over time with different prompts, with one-shot? One-shot is where you give it an example of input, output, and in your prompt, and it helps the model perform a little better. How changing various parameters affects the output, getting and collecting user input. So that governance is quite important as well. Chain of reasoning and agents are very powerful here as well. So for some prompts, not necessarily in RAG, but in some other cases, maybe RAG with code, for example, agents can be quite powerful, or chain of reasoning, or chain of reasoning with code. So I've mentioned, for example, that these models really don't know math, for example. But a good way to get around it is to get a model to explain step by step what it's doing. And this is done through prompting, right? And to generate Python code for it, and then to execute the code. So models can't really execute code, but you're taking the code generated by it to execute it step by step, and you're feeding it to the next prompt. So if you want to do a bit of fancy math, or you want to have a model that, I don't know, does costing, prices, sizing, that kind of stuff, the chain of reasoning agents and prompts really, really help. You can also cache embeddings and responses, which is quite important, especially if you think about the performance here. You also want to make sure you're not really ingesting the same embedding hundreds of times. So you want to think about how your caching and deduplication is going to look like, and how your personalization and conversational memory database might look like as well. Some of the AI models as a service do provide conversational memory in the API, but maybe you want to build your own conversational memory database as well. Think about the algorithms, moving window, and so on for that as well. Streaming responses is also important, and optimizing for performance. You may want to start with, here's the results from the vector database instantly, right? And then you stream the output of the LLM. And don't go overboard with your model as well. A fine-tuned 13B model might even perform better than a poor 70B one in terms of the quality of the output, or might perform well enough to justify using that instead. So just if you think, Cullora, whatever, models quantized, 70B needs, 80 gigs of RAM, and the 13B might need 13 gigs of RAM. It's like, you can run 4 or 5 of these for the price of 70B one. So it's really quite let's say, performance drop when you move to a 70B. Well, calling third-party functions or APIs for reasoning is also important. Remember, LLMs are terrible at reasoning or prediction. In fact, don't use them for prediction at all. They'll predict the next word in a sentence. They won't, predict the next number in a time series, which is, a big issue if you're trying to use it for that. Consider calling other models, or multimodal is also something to consider when you're designing these kind of applications. Also think of fallback techniques. This model didn't perform well on this query. Maybe I'm going to try a different model or a default answer instead of letting the model just go off and coming back with whatever it can. So how are you scoring those results? So maybe there's an evaluation loop in there as well. Let's call scores the output, and it falls back to a different model or to a default answer. Think about scaling your API as well. So most of these applications I'm using Fast API. With Python is quite scalable, but think about things like, rate limiting, for example, because these models are slow, expensive, and if you're running your own model, you're really queuing a lot of requests on a single GPU. If you have multiple GPUs, then, your parallelization is based on the number of GPUs or the number of models that fit within video memory at any point in time. For your API, you really want to think about asynchronous responses, streaming, parallelization, processing, GPU acceleration, including things like embeddings, and generating your own API using open API, so it's much easier to regenerate every time. Now, the interesting part is, a lot of these, sentence transformers, if you're using them, you want to think about the performance of embeddings as well. Because every time somebody searches, there's a vectorization happening, right? And every time somebody loads a document, there's another vectorization happening. And those can be blocking calls. Maybe you want to move those activities to a separate microservice. And I found that TGIS, the model serving framework from HuggingFace, is quite useful for a lot of these model-related activities. It's written in Rust. It's containerized. It can be very useful for scaling. You can find this talk on GitHub, so go to github.com, Weaviate and Shipitcon, scaling Retrieval Augmented Generation, or on social media. You can follow me on Twitter, YouTube, or LinkedIn for more. Thank you, and have a great day.